All right, everybody, it's about 10 o'clock. I think I'm going to go ahead and get started here. Welcome to Thursday, and I hope that your week is going pretty well. We don't have a fire drill today, thankfully, so we can get right into it. Couple quick announcements. First of all, don't forget that there's no homework due today, but the current homework assignment is actually due tomorrow. So tomorrow night. So what I'm going to do actually is I'm going to set up another extra office hour. Extra office hour tomorrow night, since we have homework due tomorrow night. So tomorrow would be Friday. And I'll go from 7 to 10. I think that ought to be a pretty decent amount. So if you have questions that we don't get answered today in class, I encourage you to stop by tomorrow night. Feel free to do that. So homework number 19 is due tomorrow. And I will also take a few questions on that. I've got a couple on the sideboard so far, and during the break, if you want to add anything else to that list, you're welcome to do that. The next homework after this one is homework 20, and that one's going to be due on Tuesday. And that's the one that I said you could probably do it in about 20 minutes. To make matters even easier for you, I'm probably going to end up doing most of it in class on Tuesday. So you really don't have a lot to worry about as far as that goes over the weekend. What you might do over the weekend instead of worrying too much about the homework is do a little studying on chapters 6 and 7. Okay, so the reason is that on Tuesday, there is going to be an extra credit quiz. This is on Tuesday. That will be in class, so you absolutely have to be here to take it. It's just like the take-home quizzes that you've done for the first two exams. This time I want to do it in class. So it'll only be like 25 minutes or something, and it'll be worth like 3 or 4 points towards your next midterm, which is coming up after Thanksgiving. And this will cover 6.3 and 6.4, which is the kernel and the range, one-to-one and onto both the neither, and then also the stuff on eigenvalues and eigenvectors, which is from chapter 7. Question?
Is it like any point you get, it's counted, or you get to get it?
I basically, every problem will be worth 1 point, and I will either give you 0, 1, or possibly 1/2. So if it's about half right, I'll give you half credit for it. So it'll be kind of 0, 1/2, or 1.
You don't have to like get the whole quiz right.
Oh, no. For each of the problems, you could get either 0, 1/2, or 1. Yeah, exactly. Anyway, so I would actually recommend over the weekend that you focus more on this homework assignment. Well, you could do the homework. You just want to get it over with. It's really quick. But the quiz might be good because that'll help you start getting ready for the exam that's coming up after the Thanksgiving break. So anyway, so that's over the weekend what I would be working on. But we've got, the first things first, we've got this homework that you need to turn in by tomorrow night. And that's kind of where we're at. Does anybody have any questions about that? If not, I'm going to jump right in and review where we left off on Tuesday. We had a little bit of a short class on Tuesday, so I'm going to try to catch up a little bit now today. We were talking about solving differential equations again. But this time, we're talking about differential equations of pretty high order. It could be an nth order differential equation for any n. And as long as it's linear, and as long as it's constant coefficient, and as long as it's homogeneous, remember homogeneous just means 0 on the right-hand side, right? The n is referring to the most derivatives that we see here. As long as we have this kind of a differential equation, we actually came up with a great idea for how to solve it. So this is how it would look in the D notation. Remember that D just stands for derivative operator. So every time you see a D, it just means take the derivative. And if I see powers of D, it just means take higher derivatives of this unknown function y. The goal, of course, the goal here, as always, is to solve for y. That's what we want to do. The unknown function y, that's what we're hoping to solve for. Okay. So we used this really ingenious idea on Tuesday about how to solve this differential equation, which was to guess the answer. Remember that somebody long before I ever came along figured out that if we use a function that is exponential, namely of this form here, e to the rx, that is a good candidate for a solution to our differential equation. Yeah, and it turns out that that trial solution that's in this box will work as long as the R value that you choose here satisfies this auxiliary equation. And the beautiful thing about it, guys, is this auxiliary equation is literally the same as the operator equation in the original differential equation. You might notice that this thing here, which is my derivative operator on my differential equation, looks almost the same, doesn't it, as the auxiliary equation. Essentially, all you have to do is change the D's into R's. That's all that you have to do. So you have this auxiliary equation right here. In some ways, the hardest part of what you have to do is you have to solve this equation, which is really a high school problem. It's a high school factoring problem or finding roots or whatever. And that's mostly what homework number 20 is going to be about, is just, you have to solve these auxiliary equations for the values of R. And for each value of R that you obtain, you get a solution to your differential equation of the form e to the rx. And then you can just simply build linear combinations of those solutions to write down the general solution. So that's basically all it is. I did talk on Tuesday about this Wronskian test. If I have a set of functions, say y1, y2, y3, and so on, and I want to know, are they linearly independent, right? Because we're talking now about trying to find a basis for the solutions to our differential equation. So the basis will consist of functions. And this Wronskian test is basically how I can make sure that a collection of functions is Li. Namely, we take this determinant here. So I lay out my functions into the top row of this matrix, and I start taking derivatives down the matrix until it is a square size matrix. Once I calculate the determinant of that, if I can find any value x naught, if I can plug in any number for x, if there's even one number for x that makes that determinant not zero, then good things happen, right? In that case, then my functions are Li, and hopefully that is going to be my basis, therefore, for my solution set. So this is just the Wronskian test for linear independence of these functions, right? Everybody with me? So that's just a quick review of where we were last time. Maybe to kind of get warmed up today, I thought I'd just practice this Wronskian test with you really quickly on an example. We're going to be seeing these expressions e to the rx quite often, as you can tell. So I thought, well, what would happen if my functions were e to the ax, e to the bx, and e to the cx? And I wanted to know if they were Li. Right, so maybe I was trying to see if these would be a basis for the solutions of some third order differential equation, okay? Well, it turns out that as long as A, B, and C are distinct, none of them are the same as each other, then my functions will be Li. And I'd like to try to show you that, show you the calculation behind that, okay? So let's see if I can do this little warm-up problem right here. I'll start my solution. When I'm taking a set of functions and I'm testing if they are Li or not, my go-to thought should be Wronskian test. I'm going to use the Wronskian test. So let's calculate the W for e to the ax, e to the bx, and e to the cx. Let's actually calculate this Wronskian. Okay, so this is the determinant of, it will be a 3 by 3 matrix, yeah? And I've reminded you here how we construct this matrix, we put these exponential functions onto the first row. E to the ax, e to the bx, and e to the cx. That goes on the first row. And now I'm going to start taking derivatives. Start taking derivatives down the matrix. So the derivative of e to the ax would be a e to the ax. And the derivative of e to the bx would be b e to the bx. And the derivative of c e to the cx would just be c e to the cx. So you just pull the coefficients down. It's not yet a square matrix, so I have to go another step further and take another derivative, which will just pull more factors of a, b's, and c's down in front. So on the bottom row here, I'll have a squared times e to the ax, and then b squared times e to the bx, and then c squared times e to the cx. It's going to look something like that. And again, the idea is if there's even one value of x that makes the determinant not zero, then the functions are Li. That's what that test says over there. The functions will be Li as long as I can plug a number in for x and have the Wronskian be not zero. I'm just curious, does anybody think there might be a good choice of a number to plug in for x here? I would plug in a number that will be very easy to calculate, and x equals 0 would be really awesome. So I'm going to try that. Now it's no guarantee that this one will work, but I'm going to evaluate this determinant at x equals 0. So I'll call that x naught. And when I do that, so I'm going to just plug in 0, in other words, for every single x. So e to the 0, as we know, is just 1. So if I just go through this whole matrix and I start plugging in 0 for x everywhere, I will just get this matrix right here. Okay. So I've plugged in 0 everywhere I see an x. And this is the matrix I have. The question is, is this 0 or is it not 0? Well, I can use my arrow method on this. Okay, so you guys remember the arrow method, I'm sure. We just recopy the first two columns here. And I can use this arrow method. The first diagonal gives me BC squared. The second one gives me CA squared. And the third one gives me AB squared. Right? And then I have to do minus. I go minus. The other way I have A squared B. And then the next one is minus B squared C. And then the last one is C squared A. And so that's what we have. The first time I saw this, I was trying like crazy to figure out how to factor it. And, there's some common A, B's, and C's here. I thought, oh, there's got to be some algebra to it. And I just couldn't get it to work out. It turns out it's kind of hard to see immediately how you're supposed to factor that. But it does factor. It's just not maybe quite as obvious as you would like it to be. I will just tell you what it actually comes out to be here. It turns out to be the quantity C minus B times the quantity C minus A times the quantity B minus A. The easier thing to do actually is to start from this and FOIL it out. And if you take this thing and you FOIL it out, you would actually get this. Okay, so don't worry too much about this step. This is just algebra to rewrite this one like this. You can kind of see, right? If I take C times B, oh, that's the first term, right? The last term, I've got a BAA, and that's with 3 minus signs. So BAA, that's this term, right? So all of the terms are actually going to be there if you were to FOIL this out. But the important thing is, if you're willing to believe me, I see people trying to do it in their head. Like, yeah, it's not quite that easy. You actually have to write it all out. Anyway, after you FOIL it out, I promise you, this is the same as all of these terms. Okay? But the key thing is that A, B, and C are all distinct. None of them are the same as each other. So C minus B, that's not zero. C minus A, that's not zero. And B minus A, that's not zero. If they're all distinct. So if they're all distinct, then these three things are all not zero, right? This whole thing is not zero. I'll just say since A, B, and C are distinct. And that's the Wronskian test. That's what the Wronskian test says. It says that as long as the Wronskian is not zero, then we can conclude by, I'll call it the W test. By the W test, e to the ax, e to the bx, e to the cx is Li. That's right. It is Li. Okay, clear enough? So just as maybe a quick little warm-up example, let's go back to actually solving a differential equation again. As a quick little warm-up example, let's just suppose that I asked you to find the general solution to, oh, let's make this equation here, d minus 2 times the quantity d squared minus 16 of y equals 0. Suppose that we tried to make this equation work. Okay. So for the solution, okay, so this is an example of what you'll be doing in section 8.2 homework. Okay. So watch how quick this is, and that'll give you an idea about next Tuesday's homework. So basically, the first thing I always do is just go straight to the auxiliary equation. The auxiliary equation, remember that's just this equation right here. How do we get it? We just change all the d's to r's. Literally the d's turn into r's. So in this case, that would be r minus 2 times r squared minus 16. And we're setting that equal to 0. Can somebody tell me what the roots for r would be here? One more time. 2,
4 and negative 4.
and 4 and negative 4, right? And guys, that's like your ABC. 3 distinct numbers. So your e to the rx's are all going to be Li. So we can make the first solution would be e to the 2x. The second solution would be e to the 4x. And the third solution would be e to the negative 4x. That's it. Right? And these are Li by the warm-up problem that we just did, or in other words, they're Li by the W test. So if you use the Wronskian test, which is what we just did right here, we showed that as long as it's 3 distinct numbers, then these functions are Li. And if they are Li, then they are going to be a basis for the solutions to my differential equation, right? And so the general solution then is, final answer to this problem is just y of x equals c1 times e to the 2x plus c2 times e to the 4x plus c3 times e to the negative 4x. That's the whole thing. That's the solution to the differential equation. All right. I'm generally not going to be asking you to do the Wronskian test part of it. You're going to be allowed to just take that as a given, right? We just proved it here for 3. But you might say, well, what would happen if there were 4 values of r? Well, then technically, we would have to do a 4x4 Wronskian and make sure that the functions were still Li. We're not going to be doing that. It's way too much tedious work, and it's just to confirm something that has already been known to be true. So generally, you won't be asked to do the W test part of it, and therefore the work that you see on the board right here is all you have to do. This is the entire solution. Change the D's into R's, solve for R, write down your basis solutions, and then put them into the general linear combination, right? That's basically the whole ball of wax. I thought I would do, is there any questions on that? Yeah, Blake.
What happens when the Wronskian is 0?
Well, if the Wronskian is always 0 for every value of x, then that means that your functions are actually LD. And that means that you don't have a basis yet. So in that case, let's say that A, B, and C were not distinct. Let's say you had a repeated root. Well, then you'd be writing the same function twice into this set, and that would definitely not be Li anymore. You'd have the same vector listed twice. So you're gonna have to do something else to figure out how to solve it. And you're asking a really good question because it's something I'm going to be explaining in just a little bit here today. Yeah, good point. Okay, so far so good, everybody? I thought I might do a quick proof of this Wronskian test. Maybe I can do it back over here. Let me see if I can prove the Wronskian test. Oh, this is erasing so nice today. You guys saw what I did, didn't you, the other day? Well, people were using those disinfectant wipes on this board and making it wet, and then it was not erasing right. So guess what I did with the disinfectant wipes? They're in my office. It's like, I'm gonna solve this problem. They're not gonna do this anymore. It's still not great, but it is getting better, I think, over time. So anyhow, let me do the proof of the Wronskian test. I actually think it's kind of a nice one to understand the proof of. It's a little theoretical, but I think it'll be nice to see it. So in other words, I'd like to prove this test down. Namely, I would like to convince you, I hope, that as long as the Wronskian of my functions is not 0, that then those functions are Li. If I want to prove that a set of functions is, or really just a set of vectors in general, is Li. If I want to prove that, right? If I want to show that this set is Li, the way I do it, as you'll remember, is I assume that there's a linear combination of those functions that happens to cancel out. So I start off that way. I start off by assuming that we have a set of, or a linear combination of those functions that cancels out. And does anybody remember what I want to show then? That's when I have a linear transformation. This is more just back to vector space theory. The definition of linear independence is that assuming that my vectors cancel out in a linear combination, then
What? See what? Yeah. That's the only-
that's exactly right. I'm not sure if everybody heard that. What Audrey said basically is that I would like to show that all of the constants must be 0, right? That they must actually be 0. I'm going to try to show you that. That's exactly right. Now remember, y1, y2, y3, these are functions. Might be e to the ax, e to the bx, e to the cx, something like that. These are functions. But what I'm going to do with this equation, guys, is right below it, I'm literally just going to take the derivative of it. Okay, so I'm just going to take the derivative of everything that I see here, guys. So I'm going to put a derivative on all of these terms. I'm just going to take the derivative of everything. So taking the derivative, we would get that. And then I'm going to do it again. So I'm going to do another derivative. On the next line, I'll have the second derivative of everything. Right? I get the second derivative of everything here. And we keep going like this, right? And I'm going to go all the way until I get to n-1 derivatives of everything. So I'm just taking that original equation and I'm calculating, just making sure that I'm calculating all of these derivatives of all of these functions, yeah. So I'm just taking derivatives of every single term. Yes.
Why is it not n? I mean, n-1 derivative plus n.
I can, if I want to, I can go all the way to n derivatives. There's nothing, I could do another line below this one where I go to the nth derivative. I could go to the 5 billionth derivative if I really wanted to. But to make this proof work, if I kind of look back at what my Wronskian is here, you see on the bottom line, the reason that this stops at n-1 derivatives is that that's what makes this into a square matrix. It becomes a square matrix already after n-1 derivatives. So it's not that we can't go to another line and do n derivatives of everything, but we don't need to. This is actually as much as we actually need to show. Okay? So I just took the starting equation, guys. I want everybody to follow this. This is mostly the rest of today is all computational. This is the one theoretical thing, which is that you start with this abstract equation and you start taking derivatives of it. And what you now have in front of you is a whole big system of equations. And I bet you know what I'm going to do with it. I bet you know what I'm going to do with it. I'm going to put it in a matrix. All right, I'm going to write this as a matrix form. Sarah?
Maybe I missed this, but how does the n-1 make it a square if n could be anything?
Well, all I mean is so let's say we have only 3 things. Okay. So if I only have 3 things, like how far down do I have to take derivatives to make this into a 3 by 3 matrix? All right, so I have to take one derivative here. And then I have to take another derivative here. Well, that's only 2 derivatives. It's a 3 by 3 matrix, but I could stop after only 2 derivatives and it was already a square size. That's all I'm saying.
Oh, okay.
Yeah. So I've just chosen to stop here, but I didn't have to. I could have written down 100 more lines below this one. But for the purposes of what I'm trying to do, I don't need to write out anything further. Okay, but I'm going to put this in a matrix. And here's how that matrix is going to look, guys. I'm actually going to put the C's over here into this column, C1, C2, and dot, dot, dot down to Cn. That's going to go into a column right there. And on the right-hand side, I'm going to have simply a column of zeros over here. It's going to kind of look like that. And then how do I fill this out so that matrix multiplication is reflecting what's on the left side? Well, I can see that, for example, the very top equation here, C1, Y1 plus C2, Y2, and so on, we'll be able to get that if we just write Y1 through Yn on the first row. If you dot that first row with the C column, you get the first equation on the left over here, don't we? Yeah, so that's exactly that one. And then on the next row, of course, I have just the derivatives of all of those. So what's happening here, and I think I'll just go straight into my dot, dot, dot here. What's happening is this matrix that we're coming up with, this happens to be the same as this matrix, right? It's literally that same matrix here. So we just keep going all the way to the bottom. We will have n-1 derivatives of everything. Okay. And what we are told here is that we are assuming that this determinant is not 0. That it is not 0. So you can think of this as there's a matrix here times this vector of constants equals 0. And we are assuming that the determinant of A is not 0, at least for one value of x. It's not 0. So since the determinant of A is not 0, okay, that means this matrix is invertible. If the matrix is invertible, guess what? You can cancel it. You can use the A inverse to basically cancel it, can't you? Right, you can cancel, so I'll just say A inverse exists. There's an inverse for this matrix because it's got a non-zero determinant. And so what we can do then, if the A inverse exists, is we can apply it to both sides of our equation. Just put it on the left of both sides of our equation. And of course, A inverse times A cancels out. And A inverse times 0 is just 0. And so what do we have here? All of the constants that are making up this vector C. If that's all just the 0 vector, then all of its entries have to be 0. That's what we wanted to conclude. That was what we were showing right here, is that all of those constants are 0. That's right. Pretty nice. Is this making any sense? So you're probably not totally aware of this, but the warm-up problem that we did today, so just as a quick note, this is maybe worth writing down just for your, more for your references than anything. Though today's warm-up plus this proof that we just did right here, plus the proof of the W test. Those two things, the warm-up was the e to the ax, e to the bx, e to the cx example, and then this was the Wronskian proof. You put those things together, you get group work number 12. So I just did group work number 12, basically is what I'm saying, from the Canvas website. We're not going to do that as a class. I just wanted to do it together with you. I am planning some group work for next Tuesday. I mentioned there's going to be an extra credit quiz next Tuesday. That'll be at the end of class. I'm going to start with some group work first. So there'll be actually a couple of group works. We haven't done number 11 yet, and we'll probably also do 13 on Tuesday. So we have a couple of group works, we'll have a quiz. Be a little bit of an easier lecture day for me, I guess. Okay, so I do want to point out that as simple as this process looks, there are two issues that can come up, and I want to address both of them. There are two big issues that we have not talked about yet. With respect to, you know, this auxiliary equation. And so the two issues are, what if the auxiliary equation has the first issue would be repeated roots. And the second issue, I mentioned this briefly last time, there is a possibility that you could have complex numbers for roots as well. So we haven't seen these scenarios yet, but they are both possible and they both do actually happen. So I need to kind of have a quick talk about what we're going to do if we see the same root multiple times. Okay, if I'm happy that e to the ax, e to the bx, and e to the cx are Li. But what if it was e to the ax, e to the ax, and e to the ax? If it was the same root repeating itself here, right? And that's all at the mercy of the auxiliary equation, right? What if the same root came up in the auxiliary equation? Then you're not going to be able to just use the same solution 3 times. That will not be Li, right? So e to the ax, e to the bx, e to the cx, yeah, that's Li. We proved that in the warm-up. But e to the ax 3 times is like having the same vector 3 times and spending $3,000 on something that you would not want to spend more than $1,000. So let's just talk about these two issues. I'm going to start with the repeated roots one. And I'm just going to kind of tell you what the story is here, guys. So if a root, if some root R is repeated k times, then we can get K linearly independent solutions in a certain manner, which I have to write down. And so I'm going to write them down over here. So how do we get our K solutions? Well, first of all, y1 of x, sure, that'll just be e to the rx. No problem with that. But if that same solution or that same root is showing up now for a second time, I can't just write e to the rx again. So here's the trick. And again, I didn't figure this out. This happened way before I came along. The trick is that you start stacking x's in front of the e to the rx. So the second solution is going to be x times e to the rx. And then if there's a third solution, you're going to stack another x. This would be x squared e to the rx. And we keep going like this. We're supposed to come up with k of them. Y sub k of x. Well, that would be x to the k minus 1 times e to the rx. That is your list of solutions. Oh boy. This other eraser here. That is your list of solutions that is going to be Li. Let's see. Well, it's not getting too good yet. So guys, I'm not going to be asking you to do the Wronskian test on this. The fact that these are Li would be proven by using the Wronskian test, but you can see what a nightmare it would be. Because taking derivatives now is not just simply pulling the r's down in front, is it? You have actually a product rule that you would have to use, and so your Wronskian matrix is going to become a mess, right? So somebody worked it out, okay, and did us all a big favor and sort of confirmed that, yeah, those things are going to be Li, so don't worry about it. And so we're not going to worry about it, okay? So we're just going to know that this works. So what we're doing here, guys, is what you're going to hear me using this phrase quite often. We are doing x stacking for repeats. So if there's repeated roots, I stack those x's in front of the e to the rx's that we already have there. Okay, so that's the first issue. I'm going to wait to do an example of that until a little bit later on. I want to get the second issue addressed though first, which is what about complex numbers? So what if we have complex numbers as roots of our auxiliary equation? In this case, the roots might be a plus or minus bi, where b is not 0. So these will be some kind of imaginary roots. They always come in pairs like this, just like they did for the eigenvalues of a matrix. If there was a complex number for an eigenvalue, then the conjugate of that eigenvalue was also an eigenvalue. The same thing happens here. You're going to get these roots as pairs, okay? And now you could say, well, I'm just going to try to create solutions the same way we've just done it before. Namely, and I'm going to call these C1 of x and C2 of x. I could just try to just do, e to the a plus bi times x. And then for my second solution, e to the a minus bi times x. This is just e to the rx for the two values of r that we have. And you might think there's nothing wrong with that, that should just be fine. We just have that as our solution. Or for those two terms of our solution. The problem is, you guys are engineers. You would like to have solutions to your differential equation that are actually real valued. Like that you could touch and feel these functions. You could actually make sense of them. Right now, the way it is right now, I don't even think I could plug this into a calculator. If you give me a number for x to plug in, So you're gonna try to evaluate E to this imaginary power. That's already a whole big conversation about what does that even mean. And so you can take Math 412 and it's all about complex analysis and learn like, what does that mean? I don't even know what that would mean. I also would have no idea how to draw a graph of this. You asked me to graph E to the 3 plus 4i times x, I'm basically lost. I don't even know. I mean, because normally you have an x-axis and a y-axis, right? But now how are you going to input like 3 plus 4i? That's not anywhere on this real axis. So I don't even know what I don't know how to draw a picture of this. I don't know how to plug it into a calculator or come up with any kind of numbers. So this is not a very happy answer. Okay, right? I wouldn't be wanting to go to my boss with that answer and hope to keep my job for very long. So, but there is a thing we can do to extract two real solutions from these two unacceptable solutions. And I'm going to show you how that works real quick, okay? It's pretty nice. So take the first one. And the first thing I'm going to do is I'm just going to rewrite it as e to the ax times e to the I bx. So this is using just the properties of exponential functions. I can certainly do that. And then for my next step, I'm going to put a little asterisk here. For the next step, I'm going to come maybe over here for my asterisk on the side. Can you guys all see over here? Right? There is a formula. I don't know if any of you have seen it for e to the I theta. Have you seen the t-shirt that has e to the I pi on it? Turns out e to the power of I times pi is equal to -1. And it's a famous formula that people like to put even on I've seen it on t-shirts in lots of places because it involves a single formula that has e and I in it at the same time and pi. E and I and pi, which are these really unrelated irrational numbers that are somehow connected by a formula. Turns out that it is based on this formula here, which is something called Euler's formula. And what this says is that the cosine of theta plus I times the sine of theta. So if I want to know what is e to the I theta, the answer is it's cosine of theta plus I times sine of theta. Has anybody seen this before? Maybe you have. It's proven using power series. And so you go back to your calculus class. There's a power series for e to the x. There's a power series for cosine of x. And there's a power series for sine of x. If you look at what all those formulas are and you stick them in to these places here, everything works. And you get a true equality out of that. So I'm not going to derive this right now. It's really better discussed in the context of calculus. But certainly this Euler's formula is a useful thing. And yeah, if you plug in pi for theta, you'll just get e to the I pi equals -1. Cosine of pi is -1. Sine of pi is 0. So that's where that formula comes from that you sometimes see people using. So I'm going to use that star equation right here on this e to the I bx term. So this is e to the ax times cosine of bx plus I times the sine of bx. So where I see the e to the I bx thing, I'm going to replace it with cosine of bx plus I times sine of bx. And I'm going to do the same thing on the bottom line. So I have e to the ax and then e to the I times -bx this time. And so if I again make this substitution, e to the ax, and then I have cosine of -bx is actually the same as the cosine of bx. Cosine is one of those even functions. So the minus sign can just be dropped. I don't have to put a minus in there. And the sine of -bx does have a minus sign on it. So it becomes minus I times the sine of bx. Let me just do a quick little double star on this one. So just the double star comment here, guys, is just that the cosine of negative of theta is the same as the cosine of theta, and the sine of negative theta is the negative of the sine of theta. So I'm using that here to simplify my expressions. Okay. Now, so far I still am in trouble. I am still in trouble because my two solutions, Z1 and Z2, they still both have I in them. That's what we were trying to get away from, right? We're hoping to come up with real valued solutions to our differential equation. Is there any way that we could get rid of that I? I want to make it go away.
You could plug in something that would make sine into 0 and then it would get rid of that term.
We could plug in a number for x here, but the problem is we're really looking for a function of x that we are ending up with for our solution, and that's going to require us not to have a specific number plugged in. Jason?
Can we add them?
Can we add them? Was that what you were gonna say? No. That's okay. You know what? That's exactly right. Guys, remember, we're talking about something that is a vector space right now. The solutions to this differential equation, they are a vector space, and so they are closed under addition. So if this is a solution and this is a solution, then their sum is just another solution. It's closed under addition. I'm going to add them together to get so you literally just imagine like adding these things down, right? The I parts are going to totally cancel out, right? And all that you'll be left with is sort of two copies of the first part. I don't really want to have the 2 in front of that, but that's okay because I can multiply by 1/2. It's closed under scalar multiplication too, right? So then that's exactly right. We are going to form y1 of x, which is going to be half of z1 plus z2. This is how we're going to do this. And what is that? If I literally add these, the I parts cancel, and I get 2 factors of e to the ax cosine of bx. As soon as I divide by 2, I just get e to the ax cosine of bx. That turns out to be what I want. That turns out to be exactly what I want. And that's only one solution. But it is one very good solution. It does not have I in it anymore. Okay. And again, this solution is just a linear combination of 2 things that are already solutions. Right? So we have 2 solutions. They're not very nice solutions, but I can add them, scalar multiply them, whatever I want with vector space operations and make new solutions from these 2. That's exactly the idea here. I'm going to do the same thing. Well, I need to get a second solution. Because after all, I have 2 roots here. These 2 roots need to give me 2 solutions. The way that you get the second one is that instead of adding the 2 functions together, what you do instead is you subtract them. Now, when you subtract them, the cosine parts cancel, right? This thing cancels with this thing if we just literally subtract them. Over here, when you subtract on the imaginary parts, you actually end up doubling the sine of bx term. But again, I can scalar multiply by 1/2 to deal with that. So what I'm going to do here, guys, is I'm going to take z1 minus z2, right? I'm going to literally subtract them. That's going to give me 2i times e to the ax sine of bx. So I actually need to divide by 2. I don't want the 2 there. But this time I actually also have to divide by I, because there is an imaginary number there on the sine terms that I don't want to have floating around. Okay, so I'm going to divide by I as well. That's still just a constant, right? So still just a number. So I just divide by I, and now what do I have left? This will be e to the ax sine of bx. That's it. That's it. So guys, what is the punchline here? The punchline, what you really need to learn, I'm just trying to derive it for you, but you don't need to remember all of this derivation. The only thing you really need to remember, right? What is really where the rubber hits the road for you guys is that if I have the roots a plus or minus bi, I'm going to make two solutions, which are e to the ax cosine of bx and a second solution, e to the ax sine of bx. That's what you need to learn right there. That's what you need to learn. Okay. Questions about any of that? Yeah, Nathan?
Will we only ever get a plus or minus bi? We won't get like a plus or minus bi and c plus or minus di.
You could certainly get another pair of complex conjugate roots, and then you'd have two more solutions with the C's and D's in them. The other thing that you can get is you can get this pair repeated. If this complex pair repeats, then you're gonna actually have to do the X stacking business even on that kind of an expression. I think we should do a couple of examples here before we take a break today to sort of show you just how big this can become, okay? Let's see if we can do an example. Example here. Let's clear it up a little bit better here. So let's solve. In other words, find the general solution to d squared minus 6d plus 13 quantity cubed times d plus 1 to the fourth times d squared times d squared plus 4 of y equals 0. And absolutely nothing saying I was going to start with an easy example. We are going to, so does anybody know what the order of that differential equation is? If I was to expand out this big operator of d's, what would be the most d's that I would ever have in this expression? I have a d squared cubed. That'd be 6 d's, right? D squared, d squared, d squared, that's d to the 6th. And then here I have another 4 more d's. That would be d to the 10th so far. 2 more, now that's d to the 12th. And 2 more, d to the 14th. Anybody feel like solving a 14th order differential equation this morning? This is exactly what we're going to do right now. Okay, this is a 14th order differential equation, right? So solution n is 14. All right, so, and by the way, I have put a differential equation of very high order on my exams before. But as scary as it might sound, I'm about to show you just how easy this is. This is 8.2. This is easy, easy, easy. The main thing is turn all the d's into r's, right? Let's write down the auxiliary equation. Right, the auxiliary equation, we just literally turn all of the d's into r's. I don't even have to think that hard, just kind of write it down. R squared minus 6r plus 13 cubed times r plus 1 to the 4th times r squared plus 4, all of that equal to 0. And now my task is to find the roots. Now, if this was literally a FOILed out 14th degree polynomial, then I would start to be nervous. Then I'd be running for my MATLAB factorization tool to figure out how to get the roots. But see, this was handed to us sort of semi-factored to begin with. And so there's nothing we're ever going to have to figure out here that's more than just a quadratic. And as long as that's the case, we shouldn't be really that afraid of it. R squared minus 6r plus 13, I can find those roots real easily, right? Use the quadratic formula. Negative b, which is 6 plus or minus the square root of b squared, which is 36, minus 4 times 13 is 52, all over 2. Okay, and then if I figure out what that is, so what is that? That's 6 over 2 is 3. And then plus or minus, this is the radical of negative 16, which would be what? 4i, which then gets divided by 2. So I'm going to write 2i. Okay, so I'm now starting to write out my list of roots. 3 plus or minus 2i. How many times do I need to rewrite down 3 plus or minus 2i? A total of 3 times because it's being cubed right here, right? So these roots are being triply repeated here. So I'm going to write them down 3 times. Just like with eigenvalues, when I ask you to write down repeats of eigenvalues, you also here want to write down the repeats of the roots that you obtain. Okay, so we have 3 of those. Then what else do we have? What's the R value for this term right here? -1. And how many times should I write down -1? 4 times. So -1, -1, -1, -1. Awesome. Okay, what is the root that corresponds here with R squared? Just 0. And how many times should I write down 0? 2 times. Okay, and then the last one, this is a quadratic as well. So if we needed to, we could use the quadratic formula. But you're really just looking for the square root of -4. And the square root of -4 is just plus or minus 2i. And so I would add that on the end there, plus or minus 2i. But again, if you ever get nervous about whether you're getting the roots of a quadratic correct, you can always use the quadratic formula to make sure that you have it correct. So these are the roots. These are the roots. Okay, so now, do we have 14 people here today? I think we do. Good. I'm going to need 14 volunteers to help me write down the general solution to my differential equation. Okay, so let's come over here and write it down. You almost need more paper just to write the answer than just the work. Look how little work we've had to write down. It's been almost nothing. Now we're just ready to write down the final answer, which is to write down the general solution here. And so y of x equals, do I have a brave volunteer who wants to take a stab at what the first term would be? You've got your roots all listed out for you here. You just have to put them now into the answer. You want to try it?
It would be C1.
C1 times
E to 3 plus 2y. No.
Keep in mind you have something over here that might help you. Because if I have imaginary roots, then I can make my solutions here, right? So I'm kind of looking at this, you're looking at this, I assume. So 3 plus or minus 2i, can you tell me what the root would be for that, or what the solution would be for that? Somebody else want to try? Nathan?
Is it E to 3x cosine 2x?
That's it. That's it. The 3. So the A is 3 and the B is 2, right? So I have 3 plus or minus 2i. I put down e to the 3x cosine of 2x. Awesome. Okay. Jerry, do you want to give me the next term? Your hand was up a minute ago.
For the next one, would it also be C2
C2.
times e to the 3x sine 2x?
I love it. I love it. Exactly. C2 e to the 3x sine of 2x. Looks great to me. Okay. Now that takes care of these 2 ones. Okay. So now I'm going to go to the next ones, and we notice that the next ones are repeating. Okay, so when we have repeated roots, right, a certain number of times, that's where we do this x stacking. Does anybody want to take a stab at the next term, Blake?
C3x 3x or e to the 3x cosine 2x?
I like it. I like it. Exactly. So I just stack an x in there to handle that repeat root. Okay. Anybody want to try the next one? Eduardo?
Got it. Is it C4 of x squared or just X?
So it turns out we don't have to stack another X yet because the root that we're about to write down corresponds to this one. And this one, we've only seen it once so far. So we're just gonna leave it as an X for now.
Oh, so okay, so it's the C4 of X e to the 3X sine of 2X.
Great, exactly. That's all it is. Just stack that X right in front of there. Sweet, okay. That takes care of these two roots. All right, do I have a brave volunteer to try the next term? Audrey?
D5. X.
Nice. C5 x squared e to the 3x cosine of 2x. Very good. Do I have a volunteer for the next term? Go ahead, Vera.
C6 x squared e to the 3x sine of 2x.
Nice. All right, we're almost halfway there. So that takes care of these two roots. Somebody I haven't heard from want to give me the next term? Now I'm moving over to here. So we don't have an imaginary root anymore. We're just going to look at the -1. Ryan?
E to the -1x.
Okay, and there's going to be a C7 in front of that. C7 times e to the -x. Exactly. So here you don't have sines and cosines. You just literally put e to the rx, which would be that one. Okay, great. Does somebody want to give me the next term? Go ahead. Yes, sir.
C8 e to the -x.
One more time.
C8 e to the -x.
Not quite. Yes.
Would it be C8 X to the e to the negative?
X e to the -x. See, it's repeating. So as we repeat the roots, we start stacking those x's.
Oh, I
Okay.
thought it's only imaginary.
No, the stacking works for any kind of repeats. Good point. Good point. Anybody want to try the next term? Who haven't I picked on yet? Go ahead, Julie.
C9 x squared e to the -x.
Nice. Looks good to me. Who wants to take the next term? Daniel? Okay, super. So we have 4 terms that all involve the -1 root. Okay. Getting there. Still not done. I need another volunteer. Is there anybody I haven't heard from yet that wants to take on the next term? The next term we have the root of 0. Somebody I have not heard from. Get everybody involved. Who haven't I heard from? I've heard from just about everybody. Jason.
Would it just be C11?
Okay, this one's a little weird. This is a little weird. It's just C11. It's really C11 times e to the 0x. Right, so it's literally just gonna be C11. Okay. Isaac, you want to take the next one?
C12 times.
C12x, exactly. We stack that x because the 0 got repeated right there. Absolutely. All right, I've only got 2 more terms to go. Do I have a volunteer for the 13th term? 13th term. Have I? Anybody who hasn't had a chance yet? Thomas, can I pick on you?
C13 cosine of 2x.
Okay, notice that on this one, there is no e part. That's just because this imaginary number does not have a real piece. The a is 0. If the a is 0, then the exponential term, it just isn't there. Right? That makes some sense? Go ahead, yes.
Well, the last one would be C14 sine 2x.
You are right on the money with that. Yes, I love it. C14 sine of 2x. Exactly right. Does this make sense? It takes longer to write down the answer than it does to actually do anything else. Because it is a 14th order differential equation, I expect to have 14 terms in my final answer. Okay, but most of that is just cookbook. The process of just, you have to remember the x stacking, and you have to remember what to do when you get complex roots to your auxiliary equation. Okay, we're gonna practice some more on this, just kind of keep it going after we take a little break, because we're going to talk about a slight variation on this problem that will require us to still do this a little bit more. But let's take a 10-minute break right now, and at about 11:15 we'll pick things back up again. Okay.
It's really expensive. It's like really expensive.
All right, guys, I think I might go ahead here and gather us all back up for what do we have? 35 minutes here or so, kind of wrap up for today. Before I do anything else, I just wanted to go back into our Canvas page just to show you something really quickly. You know, a few years ago, I was teaching this class and a student said to me, "Oh yeah, the math was great, loved everything. But you know, I would like to see how this is supposed to help me with my engineering because I have lots of engineering students." And so, you know, I actually decided that that's actually a very good point. And so I put together this little thing, and you're not going to be responsible for this, so don't worry about it too much. I just want to show you in the special handouts folder. I have this picture that's called Engineering Applications. It's just a JPEG picture. You may not be able to read this all that well, but I've got sort of a two-part handout here. And again, you don't need to take any notes. I just want you to see that if you take some kind of a mechanics course, you'll have lots of applications of engineering in there. And one of them is for a oscillatory behavior of a mass that's on a spring. So you have some mass M that has some spring constant K, and you want to figure out the motion of this mass as a function of time, right? Well, it turns out that there's a differential equation for that involves whatever the spring constant is and whatever the mass is, and it is just a second order constant coefficient linear homogeneous differential equation. So it's in this box right here. And so you can see that, well, you can find the roots, right? The roots of that quadratic equation. And then depending on whether the roots are complex numbers or whether they are repeated real numbers or whether they are two distinct real numbers, you get different behaviors of how this mass will oscillate as a function of time. And so there's, of course, you have to plug numbers in for the C and for the K and for the M in order to figure out on your specific scenario which case it is. But that's essentially an application of what we've just been learning how to do today to a real world problem in engineering. There's a similar analysis that you can do for a circuit. The circuit that has a resistor and a capacitor and an inductor in it. And there's some electromotive force. There's a battery here, right? Creating a circuit going around this thing. And again, there is a differential equation that will describe how much charge is on that capacitor as a function of time. And based on this differential equation, which I'm guessing many of you will see again, well, certainly some of these things you're going to see again in your engineering classes. You can try to mathematically solve it again. This one is actually not homogeneous. So you see on the right-hand side, we do not have zero here. So you might be wondering, well, what am I going to do if there's a function on the right-hand side of my differential equation? That's the very next thing I'm going to teach you guys. So at least for now, we've been working with homogeneous differential equations like the one up here, right? But of course, for the real world applications, there will be non-homogeneous ones as well. But I just wanted to throw this up here. It is in Canvas for anybody who wants to spend a little more time looking at this. Maybe you'll print it out for your engineering classes for the future. It might be useful to you. But we're not going to focus, of course, in this class quite so much on the engineering side of it because I'm here to teach you math. So, but I think it's nice to see where this stuff actually comes up. Okay, so that is in Canvas for you to explore. I'm happy to talk about it in my office as well if people have interest in that. But I want to get back to what I'm supposed to be doing here, which is talking about math. There were a couple of problems on the homework for tomorrow that ended up on the board over here, and I thought I would do a little bit with this just because this section 7.3, as you know, I didn't really lecture on it. I had you guys watch about a half-hour video for me last weekend, and I do want to thank you for doing that. But I think it would be nice to just make sure everybody's on the same page about this. These questions are going to give you a matrix, and just ask you whether it is diagonalizable or not. So the first thing is I just want to remind you that diagonalizable is just another word for non-defective. Non-defective. So they're really just asking you, is the matrix defective or non-defective? If it's not defective, if it is diagonalizable, then in the video that you guys watched, I explained how you can find a couple of matrices S and D, such that S inverse times A times S is equal to D, right? So that was in the video. Remember, you're not going to be canceling the S and the S inverse. You can't do that. If the two matrices S and S inverse are not right next to each other, they can't be canceled. So we're not canceling them here. I'm not trying to say that A is equal to D, but I am saying that we can diagonalize A with that equation and sort of relate it to D in that manner. Okay, so I'm going to remind you here in a minute when we do this problem how you figure out what S is and how you figure out what D is. Okay, so the first step though is to try to find the eigenvalues and eigenvectors of the matrix. And I have a feeling one reason why this problem might have ended up on the whiteboard over there is because this matrix does not have a single zero in it. And when you're thinking about doing your eigenvalues, you know, normally you like to do cofactor expansion along some favorable row or column. And generally it would be nice if there were some zeros in the matrix, but I don't have a single zero in this matrix anywhere. So it's not, that does not bode well in terms of trying to actually do cofactor expansion. So there's actually a clever way to get the eigenvalues and eigenvectors on this problem. It's a one-time only kind of trick. So I don't want you to think, oh, well, now I've got to see a lot of these kind of problems. Not really. Most of the time you'll see problems like this one, where there's some nice zeros in the matrix that we can take advantage of. But in this case, yeah, this is just not fitting the bill of kind of most of the examples I've shown you where we have lots of zeros in the matrix. Can anybody, just by glancing at this matrix, tell me anything about it that's maybe noteworthy? Audrey?
Well, I was kind of confused because I didn't know if you could cancel rows out before you started anything, or if that made it wrong, or if you could only do that when you have a null space.
So it's a good question. She's asking, can I do EROs on this matrix? And she's absolutely right to be worried about that. It turns out that if you do EROs on your matrix, you will mess up the eigenvalues. Okay. However, having said that, I will point out that we could do EROs and bring a row of zeros, or actually two rows of zeros into this matrix, right? So does that tell you anything about the matrix itself? Jason?
Like the set of vectors are scalar multiplication.
One more time?
Or they can be expressed as, they can be expressed in terms of the other.
I'm just looking for something about this matrix, just a very superficial thing. If it row reduces to a row of zeros, do you have an idea?
Would it mean that there's gonna be two free variables?
There will be two free variables, but before I can get free variables, I have to have an eigenvalue around. Ultimately, I'm trying to get to the issue of what are the eigenvalues here. But before I get to that, I just want to know if I have a matrix. You're all noticing the correct thing, which is that I'm going to get rows of zeros when I do EROs. What does that tell you about the matrix? I'm looking for sort of just one word. Yes.
The matrix is linearly dependent, or linearly dependent, which means it's invertible.
Is it invertible? Or is it not invertible? It is not invertible. It is not invertible because when you do EROs, you get a row of zeros. That means the rank of this matrix is not going to be 3, right? You're going to have a lower rank. So this matrix is not invertible. Of course, that then means that its determinant is 0. Did we have any facts about the eigenvalues that was related to the determinant? Back to chapter 7 again. Remember the fun facts? Thomas?
The sum or the product of them is equal to the determinant, here, which one?
Does anybody remember, do I add these or do I add the eigenvalues or do I multiply the eigenvalues to get the determinant? Multiply, it's multiply, right? It's, if you add the eigenvalues, you get what's called the trace of the matrix. In this case, we are going to multiply our lambdas and come up with 0. So I have 3 eigenvalues because it's a 3 by 3 matrix and their product is 0. Does that tell you anything about what one of the eigenvalues must be? 0. Okay, so we do know at least that 0 is an eigenvalue. Now, we don't know if it's repeated or not. Because I could have the 0 1 time or 2 times. I really can't have it 3 times because let's just look at the other fun fact for a minute. When I add up the lambdas, I have to get the trace of this matrix, and the trace of this matrix, if you add the trace here, you just get 3. So the lambdas have to add up to 3. One of them is 0. So these are the fun facts right here. One of my eigenvalues has to be 0. But I'm still a little bit in the dark about what the other 2 would be. I know that they have to all add up to 3. But, well, there's lots of ways to get the other 2 to add up to 3, right? So I've got to be a little careful. So here's the trick. The trick, my friends, is to actually first just work on this eigenvalue. Let's not worry about what the other lambdas are quite yet. Let's just work on this eigenvalue alone. So I'm going to do the null space of the matrix that I get when I subtract 0 from the main diagonal. In other words, the matrix that I get when I do nothing. I just have the same matrix again, right? I'm going to literally do nothing. And now, guys, you can, of course, cross off 2 rows. That's what people were noticing earlier. And you're absolutely right that if we now set up our unknowns as x, y, and z here, we could set z equal to t. We could set y equal to r, both of those being free, like usual. And then I have to figure out what x is by using the first row of this matrix. Well, I have an equation here that maybe I can use. Negative 2x plus y plus 4z, that should be 0. Okay, so if I want to solve this for x, I'd have to move the 2x to the other side and then divide through by 2. So I'm going to kind of do that quickly in my head if you guys don't mind. I believe, and you can correct me if I get it wrong, but I believe it's going to end up being 1/2 of r plus 2t. Okay, so that's the x value. Right? And from here, I can now bust out my variables. I can bust out my variables. So I'll get, when I bust out the r, I'm going to get a 1/2, a 1, and a 0. And when I bust out the t, I'm going to get 2, 0, and 1. Okay, so I bust out my variables and I get that. Now, here is where we actually can make a really powerful conclusion. When we were talking about eigenvalues pulling their weight, right? I always kept saying, well, the matrix will be non-defective as long as every eigenvalue pulls its weight in terms of producing eigenvectors, right? And we made a passing comment, this was about a week ago, we made this passing comment that, well, I wonder if an eigenvalue could overpull its weight to make up for another eigenvalue that came up short. And I made the remark then that no, that cannot happen. An eigenvalue cannot overpull its weight. Which means that if this eigenvalue has produced 2 eigenvectors here, it has to have a weight of at least 2, a multiplicity, as I called it, of at least 2. This lambda equals 0 is really twice, at least twice. Are people with me on that? This is not normally how we figure this stuff out, right? We don't normally first find all the eigenvectors and then go back and say, well, that must mean that we had a repeat of that eigenvalue. But in this case, it's actually quite helpful to know that 2 of these lambdas are 0. And so what would the third lambda have to be? right? The other lambda then would have to be 3 because the three of them together, they add up to 3. Right? So by the way, do we know yet if this matrix will be diagonalizable or not? I think we do. I think we absolutely do. Every eigenvalue is pulling its weight. And this eigenvalue is not repeated. So even without doing that eigenvector, I already know there's going to be an eigenvector there. As long as the eigenvalue does not repeat, it will be guaranteed to pull its weight. It's only the repeats that you get nervous about, but this repeat, which was 0 twice, did pull its weight. Right? So that turned out to be very good. Okay, so I need a little more room actually to do the other eigenvalue, which was lambda equals 3. For that, I have to subtract 3 from the main diagonal and do a null space here. So let me give myself just this space to do that with. I'm just going to subtract 3 from the main diagonal. I get -5, 1, and 4, -2, -2, and 4, and -2, 1, and 1. So make sure everybody's with me on that. So what I've done is I've subtracted 3 from the main diagonal of my matrix. Okay, and remember that this matrix is never invertible. You have to be able to cross off a row somehow. I'm just going to get rid of the first row. Doesn't really matter which row I get rid of, but I'll cross off the first row. And then I think what I'm going to do, I am going to do an ERO here, guys. I'm going to take the second row and put it up on the top, but I'm going to cut it in half first. So I'll divide through by -2. So I just get a 1, a 1, and a -2. And I'll leave the bottom row, I'll put it in the middle. My row of zeros down here on the bottom. Okay, and now I'm going to take 2 times the first row and add it to the second row. So doubling the first row and adding it to the second row should give me something like that. Okay. So this is just ERO business again, way back to chapter 2. And that should be it. And this is, of course, this we can cut down to a 1 and a -1. We want to do it that way. And now we're in business. We've got a pivot here. We've got a pivot here. I'm just going to let z be the free variable t. And once I know that, then I back substitute for y. Let's see, what do we have here? Y minus z is 0. So y is equal to z, which is t. Okay, and then finally, from the top row, I've got an equation for x here. So x plus y minus 2z is supposed to be equal to 0. And so let's see if we can solve for x here. X is going to be 2z minus y. 2z minus y is actually also t, I think. Yeah. So t is what we get. And I'm going to, as usual, bust out my free variable and get my eigenvector, which in this case then would just be 1, 1, 1. So that's after I bust out the variable. Okay, so what do I have? I've got 2 eigenvectors here. Let's call this one V3. So I've got the first 2 eigenvectors over here that corresponded to lambda equals 0. And then I've got the third eigenvector over here, which is V3. So the only thing left to do, is everybody with me? Okay. The only thing left to do is to write down S and D. It says if it is diagonalizable, right, which it is, then we're going to find S and D. And this is the part that was in the video that I watched. Do you guys remember how to do it? Audrey?
Well, never mind.
No, sir?
No, I'm not.
No worries. The nice thing here is we can just write it down. Nathan?
Yeah, this is just vectors. And then you put the
How do I put them into S?
columns.
Okay, I put them in the, does it matter what order?
Typically, no, based on which order it's done.
Correct. Okay, so he watched my video. Awesome, great. So yeah, if I just lay these out, 1/2, 1, 0, right? and then I could do 2, 0, 1. And then 1, 1, 1. Those are just the eigenvectors directly into the columns of S. And the point was that he was making is that I could put these in a different order. But if I chose to do them in a different order, then I've got to be careful that the D values are in the right order as well. Can somebody remind me how I do the D matrix? Somebody maybe I haven't heard from. Julia?
You put the lambda values across the diagonal, but it has to correspond to the order you put the vectors in.
Exactly. So I noticed that the first two vectors were corresponding to lambda equals 0. So I would put zeros for those. And then the other eigenvalue was 3. And that corresponds to the third column. So this would be your diagonal matrix. I sometimes will just leave the rest of the matrix empty. And that way I can really focus my attention on the diagonal values. If I write anything like this down, you could just always assume that the blank spaces are just zeros. It's a reasonable thing. Okay, so is everybody with me on this? Understand the process? Okay, so that's number 9. For number 11, which is the one right here, I'm going to this one's more of a traditional problem. We don't have anything too bizarre to deal with. We really just want to go through the usual process of subtracting lambda from the main diagonal of the matrix. So I'm going to do that here. Be something like that. Okay, so subtracting lambda down the main diagonal. And this time I think we can go ahead and do a regular cofactor expansion. Does anybody want to suggest a row or a column that I should use here for this matrix? First row, got a lot of zeros up there, right? So I'm going to take the first row, and I've got my 4 minus lambda to start off with right up here. So I'm doing row 1, expand row 1. So I have 4 minus lambda. And then I have to take that and multiply it by the 2 by 2 minor that is with the 1, 1 position. So that's down here in the lower right corner of the matrix. So that's negative 1 minus lambda times 1 minus lambda. And then we would have to do a plus 2 on the end of that, like so. All right. And then I don't want to multiply this all the way out. As you remember, it's better to keep it factored. But the part in the brackets is just a quadratic. So I'm going to go ahead. I'm not too nervous about multiplying that much of it out. If I expand out the part in the brackets, I'm going to get my lambda squared there. And then I'm going to get a plus lambda and a minus lambda for the outer and inner terms. Those cancel. And then I just have a minus 1 and a plus 2. So it becomes a plus 1. Okay. And so my lambda values would be what? 4 and plus and minus I, right? If I solve lambda squared plus 1 equals 0, you would get we do get imaginary numbers here, right? Does that look okay? All right, great. Can we decide already whether this matrix will be diagonalizable or not? We already can, right? And what would we conclude? That it is, right? Because we have no repeats here. If there's no repeated lambdas, then it's definitely diagonalizable. And in fact, if we want, we can get kind of bold and put down our D matrix right away. There's no reason why we can't just do that. And if you're sitting on an exam with 30 seconds left to finish, I'd write that down. might get something for it, right? So, yeah. So there you go. All right, and so let's see. So that's my D matrix, and we do need to find the corresponding eigenvectors, right? So I have to find the corresponding eigenvectors that go with these. So we would have to do lambda equals 4. I think I'm going to let you guys try that one. Is that all right? So you just subtract 4 off of the main diagonal. So this one won't be so bad. You'd just be doing, I'll at least get it started here. You're going to have to take a null space of, well, it's going to be 0, 0, 0, and then 3, -5, -1, and then 0 and 2 and -3 is what it's gonna end up being. The subtracting 4 from the main diagonal, I think that should be right. And of course, we've already got a row of zeros there. We can kind of assume we've crossed that off. And then you've got your pivots here and here, okay? And at this point, you know, you just have to solve for X, Y, and Z. Z, of course, is free. So that one would be T. All right, and then I have to solve for Y. I do know that 2Y should be equal to 3T. So Y would be what, 3/2 of T? Y is gonna be 3/2 of T. I guess I'm just doing it. Okay, I was just gonna stop it. This is what always happens to me. I get excited and I'm just doing it. Okay, so if I can continue with the middle row here, right? 3x minus 5y minus z is 0. I just want to solve for x. This is a little bit of a messy fractions thing, I think. So 3x is 5y plus z, which would be 15/2 of t plus t, which is actually 17/2 of t. And then I have to divide that by 3. So to get x, I would divide by 3, which would give me 17/6. Oh, times t, times t. 17/6 times t, so that's what goes up for x here. 17/6 times t. So I'll go ahead and bust out my first vector here, v1. When I bust out the t, I'll get 17/6, 3/2, and 1. Now, I think in the back of the book, when you look at the answer to this problem, you'll see that the first column in the back of the book is going to be 17, 9, 6. And that's just because they wanted to clear the fraction. You can always take an eigenvector and scalar multiply it up by any scalar you want. Now, if you just multiply this through by 6, you'll get another equally good eigenvector to get rid of the fractions, but you don't have to. You can certainly leave it like that. And in fact, I will just leave it like that. I'm going to start building my S matrix here. 17/6, 3/2, and 1. Okay, so that's the first column of S. Again, be sure to get your eigenvalues and eigenvectors to be lined up, as you can see here. Okay, that would be the first eigenspace. And then let's look at the next one. The next one corresponds to what? Lambda equals I? Do lambda equals I here. This is good. Practicing the complex numbers, I think, is a good thing. So I'm glad that we're taking a look at this one because this takes a little bit of care when we have complex numbers in the problem. We're going to do a null space again. That's all that we ever do. It's just null spaces to find these eigenvectors. And what matrix am I looking for? Well, I want to subtract I from the main diagonal, right? So if I subtract I, I'm going to have 4 minus I, 0 and 0. And then 3 and -1 minus I and -1. And then we're going to have 0 and then 2 and then 1 minus I. So I'm just subtracting I all the way through the main diagonal here. And again, we get to cross off a row for free because we know this matrix is not invertible. So I have to be able to cross off a row. Try to cross off a row that you don't want to have to deal with. Okay, I'm actually pretty happy with the first row. I would not cross off the first row. I'd probably cross off the messiest looking row I could find, which would be in this case the middle row. I'm just imagining that I'm doing the EROs. If I do EROs, I must get a row of zeros eventually. So let's just go ahead and grab that middle row and wipe it out. Okay, essentially wipe that out. Now, I want to show you guys, this is really going to be slick. My unknowns X, Y, and Z. The first thing I want to point out is that the first row is a very nice equation. The first row is just what? 4 minus I times X equals 0. Because there's no y term and there's no z term. So what do you know about x? It's 0, right? So you just solve this for x and you get 0. Look all right? So that's just 0. And then the third row talks about y and z. But do you guys remember when I only have two variables, or sorry, two numbers in a particular row, I can use this thing I keep calling the A-B trick? You can use that here, right? This third row is really 2y plus 1 minus I times z equals 0. And the way that my little A-B trick works is you just swap these coefficients for the y's and the z's, and then you do a sign change on one of them. So let's just do y equals 1 minus I and z equals -2. You can certainly check that if you put 1 minus I right there, and if you put -2 right there, that it will cancel out to 0, right? So this is this trick, and it just saves you from having to do complex numbers in your free variables and all that. It saves you some of the mess of solving this. Okay, is everybody okay with this? I know that previously I only showed you the A-B trick on a 2x2 matrix, but you can think of this as only being 2x2. Once you've figured out that x is 0, then the whole x part of the matrix doesn't even matter, and you're really just playing with this part. It's as if it was only a 2x2 matrix, and this little switching trick thing can totally be used immediately for that. So that gives me y and z, and that is that. I'm just going to make this into my vector then. So this just becomes v2. All right, that becomes v2, and then I can come back over to my S matrix here and put that eigenvector. So I would have 0, 1 minus I, and -2 in the middle column of S, right? And then do you guys remember what I can do for the other eigenvalue is -I? Do you remember how I can just, without doing another null space computation, that we can go straight to the eigenvector? Eduardo?
You just put the signs of I.
You just do a sign changes only on the I parts. So the fancy way of saying that is we conjugate the vector. So you take this vector and you conjugate it in the sense that anything that's imaginary gets a sign change on it. So the 0 just stays 0. The -2 down here just stays -2. It's only the imaginary part that changes sign. So the 1 minus I turns into 1 plus I, and that's it. And we can just come back over here and fill in those values. Audrey.
So with the, if you have done it the other way and see.
It would have come out at least to a multiple of this. It would have been a multiple of this one. That's very true.
Z is free, right? You'd say Z.
Z would be free, we'd call it T, right? And then, so if you did it that way, you'd probably have Z turning out to be a 1. Because when you bust the T out of Z, it would just be 1. But remember, we don't really care if we have a scalar multiple of an eigenvector. It's a perfectly good eigenvector. And
When you did the A-B trick and you swapped the sign
yes,
on the 2.
I
you
did.
gotta swap the sign on the like -1 plus I.
I could have. This could have been -1 plus I, and this could have been 2.
Okay.
Yes, that would have been fine. It honestly is a 50-50 coin flip as to which one you prefer to do. Doesn't really make a difference. Yeah.
Why is that conjugate trick?
For this one,
Yeah.
I stated that in class as a theorem. I would have to have another 15-20 minutes down in my office hours. I could show it to you. It's not a quick, obvious thing.
What chapter?
This is all in chapter 7. This is just straight eigenvalue, eigenvector theory. So yeah, that is something I didn't derive. I usually like to derive most things in this class, but once in a while I have to just sort of for the sake of time, just say, here's how we're gonna do it. So guys, are we comfortable with this answer over here? I have been known to have problems on my exams that involve S's and D's that have imaginary numbers in them. So you definitely want to be comfortable with that. I think these were two, I don't know who put those problems on the board over there, but these are probably the two best problems I could have suggested that we look at to go over. So guys, we are about out of time. I want to tell you, so on Tuesday, we're gonna do a couple of group works and a extra credit quiz at the end. Also, I am going to have some video again this weekend for you to watch. I know it's a lot, but I just am a little bit behind. I've just been trying to catch up a little bit. So be on the lookout for that. I'll probably send you an email about it over the weekend, and hopefully you'll enjoy it. It's from section 8.3 on annihilation. So, all right, that's all. Thank you so much, and I look forward to seeing you soon. Office hours, if you need help, feel free to stop by. Have a great day, everyone.